Hello, here I am with a specific kind of 2D motion, that is circular motion, which is important for all the students whether they are preparing for JEE or for NEET. This is also helpful in different chapters of physics. So let us start.
One more category of 2D motion, which is circular motion. Now I am going to analyze this kind of motion. So first let us consider a particle P which is moving along a circle. I am taking here x-axis as the reference and particle at any moment is at this location. So how position vector of this particle can be located? How it can be represented? R. If it is making angle theta with the reference that is along x-axis, then position vector r can be written as r cos theta, where this small r I have taken as radius of circle. So this is r cos theta I plus r sin theta j. This is how position vector can be represented in rectangular component forms. One very interesting thing I am going to introduce now, which is one different kind of coordinate system, that is known as polar coordinate system. We were comfortable with using the Cartesian coordinate system, but for curvilinear motion sometimes it is very convenient if we use polar coordinate system. So first let us see what is polar coordinate system. I am introducing this now, which is polar coordinate system. I am not going into detail of this coordinate system, which is a part of mathematics. The only thing that we should know is how it can be used in a physical situation. So polar coordinate system is a coordinate system. Again, as you know, for any coordinate system there must be rectangular reference axis. So here the axis should be along the radius, that is the radial axis, and along the tangent, that is tangential axis. Symbolically, it is represented as ER. This is unit vector along radius, radially outward. If I want to denote it on the diagram, it will be like this. And other has to be E theta. E theta or ET both can be written here because this is along the tangent. But for tangent, if you see, it can have two directions. One can be in this direction and other can be in this direction. So it has to be along the increment of theta, which makes E theta to be along this direction. So this is our E theta, and radially outward direction is for ER. This is now very convenient if we want to represent position vector in polar coordinate system. That simply can be written as, because a vector has to be represented by its magnitude and its direction. So that will be r, which is the magnitude of position vector, and the direction, which is UR. As you can see how simplified this looks. So polar coordinate system is used whenever curvilinear motion is there. That would be more convenient. Now let us see how we can get velocity term, because as we know, velocity has to be dr by dt. We are writing the instantaneous velocity, that will be equal to dr by dt. So now we have to differentiate the expression given here. Can we differentiate it in this form? Is it possible? Of course this is possible, but beyond the scope of our syllabus. So while differentiating or integrating, we cannot use polar coordinate system or any other coordinate system. We have to use only the Cartesian coordinate system, in which the reference axes are not changing with time. As you can see, when time changes, direction of ER and E theta will change. When particle is here, this will be direction of E theta, this will be direction of ER. When particle is here, this will be direction of ER, this will be direction of E theta. So it will continue changing throughout the motion. And for us, at this stage, it is not possible to integrate or differentiate a variable vector. What we can differentiate is only the magnitude, not the direction. Vector calculus is not in scope of our syllabus. So while integrating or differentiating, we have to represent strictly only in Cartesian coordinate form. Now I am going to derive the velocity, which we can get by differentiating this term, which is the position vector. So let us see what we get. V can be written as dr by dt, and r is r cos theta I plus r sine theta j. If now we differentiate it, on differentiating this will come as r being radius of the circle and a constant, it can be taken outside the differentiation sign. And now this is differentiation of cos theta with respect to t. So that would be minus sine theta. Of course, d theta by dt has to be written here because we had to differentiate with respect to time and I. For sine theta, it will be r already I have taken outside, so it will be cos theta into d theta by dt j. If you take d theta by dt as common, so it will be r d theta by dt minus sine theta I plus cos theta j. Now let us see what this term is, minus sine theta I plus cos theta j. If you consider the circular motion, I am drawing it here again for the reference. This was our x-axis, y-axis, and what about UR or ER? We can write both UR and ER as unit vector along radius. Similarly, U theta or E theta or UT or ET all can be written for unit vector along tangent. This angle we had taken as theta. So can we represent ER and E theta in terms of I and j? Of course we can. So ER can be written as, since it is a unit vector, its magnitude has to be 1. So that can be written as cos theta I plus sine theta j. Similarly, E theta can be written as minus sine theta I plus cos theta j, which is the same as unit vector along tangent. If you look at this, so we got here, this is r d theta by dt can be written as omega, and then this term can be replaced by E theta or Et. What does it represent? Velocity always has to be along the tangent. In no way it can be in any other direction. Whatever be the kind of motion, any type of curve on which the particle is moving, at every moment velocity has to be along the tangent. This is clearly shown from here, because we had started with an arbitrary moment and with an arbitrary position and got velocity, expression of velocity as the velocity along tangent, because we got this unit vector associated with the magnitude which is equal to omega r. So now from here we can say that magnitude of velocity will be equal to omega r and its direction has to be along tangent. This is very important result. Velocity always should be along tangent. Whenever direction of tangent is known, that has to be direction of velocity. Okay, now come to the acceleration term. Again, this velocity has to be differentiated. But now one problem is there. While differentiating velocity, as you can see in expression of velocity, there are two variables involved. One is theta and other is this term omega. Now, it is possible that omega is also variable. See, theta has to be variable always because it is a curvilinear motion. So, orientation must change with time. Theta has to be a variable in case of curvilinear motion. And omega, it can change or cannot change. It depends on whether the curvilinear motion is uniform or non-uniform. But of course, there is a possibility that omega is also a variable. If two variables are there, how do we differentiate then? You all must be knowing. First take one quantity as constant, differentiate the other. Then take second as constant and differentiate the first. In same manner, I am proceeding now. So it is equal to, first I am taking r omega as constant. So this being constant, I have written as it is. And then differentiation of sine theta, that will be equal to cos theta. One minus sign is there. So it is minus cos theta multiplied with d theta by dt I. Another is differentiation of cos theta, that will be minus sine theta d theta by dt j. In the next term, we have to take the second term as constant and differentiate omega. So now I am differentiating omega. R being constant can be written like it is, and this is d omega by dt now. Has to be multiplied with minus sine theta I plus cos theta j. As you can see what this term is, if you take minus sign outside, it will come out as cos theta I plus sin theta j. And what about this term? Minus sin theta I plus cos theta j. This is E theta. So now we got two direction accelerations which can be written as, now I am taking minus sign outside the bracket. So it can be written as minus, I have taken outside, r omega is already there. That will be cos theta I plus sin theta j. Another term being plus, this time it is d omega by dt into r. And it is minus cos theta I plus sin theta j. Now what is this? Cos theta I plus sin theta j. Can it be written as ER? Of course it can be. And what about this term? It can be written as unit vector along tangent. So we had started with velocity that was necessarily along tangent, but we got acceleration in both the direction along tangent as well as along radius. So it can be written as minus omega square r ER plus r. Now d omega by dt is rate of change of angular velocity, so that has to be equal to angular acceleration, which is represented by alpha. So r alpha et. So these are the two terms we got in our acceleration. First is in the direction opposite to radial vector. So it has to be centrally inward, because direction of ER is radially outward, so it has to be radially inward. This is called centripetal acceleration because its direction is along the center. What about this? This is the tangential acceleration, which is along tangent. So now we got two kinds of acceleration. First is tangential acceleration AC, magnitude of which is equal to omega square r. Now as we know, omega can be written as v by r, so this can be written as v square upon r as well. This is very, very important. Now let us see one more thing, that if it is a curvilinear motion, in no manner omega can be equal to 0, because if it is a curvilinear motion, theta necessarily has to change with time, and if theta is changing with time, omega cannot be equal to 0. And we can say that AC also cannot be equal to 0 because it is omega square into r, and both the terms are non-zero here. So centripetal acceleration cannot be equal to 0. If it is a curvilinear motion, what does it mean? What is the function of this centripetal acceleration? See, acceleration has two roles. Either it can change magnitude of velocity or it can change its direction. So acceleration is responsible for change in velocity, either its magnitude or direction or both. So what this can do, because direction necessarily has to change if it is a curvilinear motion, and if it is a curvilinear motion, centripetal acceleration to be there. So what does it do? It changes direction of velocity. This is responsible for change in direction of velocity, and it cannot be 0 if it is a curvilinear motion. It is essential. This is the reason why on seeing just a circular motion, you start writing centripetal acceleration, centripetal force, because of course it has to be there. If it is a circular motion or even any kind of curvilinear motion, centripetal acceleration has to be there. What about this tangential acceleration? Tangential acceleration we got as alpha r, which is equal to d omega by dt into r. Now as you know that omega can be constant as well, because if it is a uniform curvilinear motion where omega is not changing with time, let it is 2 radian per second, so it continues to be moving with 2 radian per second, in those cases this term will be equal to 0. So this can be equal to 0 if omega is constant, and if it is not constant, then it won't be equal to 0 if omega is changing. So this is what. So now what is the role of tangential acceleration? Because already we have seen that centripetal acceleration is required for change in direction of velocity. So what it does? It is responsible for change in magnitude of velocity. This is responsible for change in magnitude of velocity. If magnitude of velocity is changing, tangential acceleration would be there, otherwise it will be 0. And if you look at its magnitude, this is equal to r d omega by dt. And omega, as you know, can be written as v upon r. So r, if you take outside, got cancelled. This is dv by dt. From here, clearly it can be seen that at is responsible for change in speed. And we all know that speed or velocity has to be along the tangent. So we can write this as well. It is equal to dvt by dt, because velocity necessarily has to be along tangent. So we had started with a position vector in circular motion and got velocity which is always along tangent. Then acceleration, which has two parts, centripetal and tangential, and saw what the roles of these two kinds of acceleration. But what if motion is not a circular motion? If it is not a circular motion, then also, since direction is changing, so centripetal acceleration has to be there, and its magnitude then will be equal to, it was v square by r in case of circular motion, but here this r has to be replaced by radius of curvature, because this time it won't be the radius, it has to be radius of curvature. And as we know, if it is not a circle, any other curve, then radius of curvature will be different at different points. So even if it is a uniform curvilinear motion which is not a circular motion, then centripetal acceleration will continue changing throughout the motion, because though v is constant, radius of curvature will change continuously for each of the point. And this is very important. You will get a number of questions in which it will be asked to calculate radius of curvature for a given curve, and this is the manner in which you have to calculate its value. Radius of curvature can be written as v square upon ac. Do remember, velocity will be always along tangent, and this is centripetal acceleration in denominator. So this has to be perpendicular to velocity. So what you have to do? You have to square the magnitude of velocity and divide this with component of acceleration which is perpendicular to velocity, because that has to be the centripetal acceleration which is perpendicular to tangential direction. In this manner, we can solve a number of questions. Let us take one example. A particle is moving in a parabolic path x square is equal to y with constant speed u. Now if you draw the curve x square is equal to y, we will get this kind of parabola. It has to be symmetric about y-axis. This kind of parabola we will get. It is x square is equal to y. Find acceleration of particle when it crosses origin. Okay, it is asking for acceleration at this point, coordinate of which is 0, 0. Also, it is asking for radius of curvature at origin. So let us start now. First thing is that particle is moving with constant speed. So from here itself we can say that tangential acceleration has to be 0, because tangential acceleration is responsible for change in speed. So it has to be 0. What about the centripetal? That would be equal to v square by rho. Now let us start with the equation that is provided. It is x square is equal to y. If you differentiate it on both the sides, that will be 2x dx by dt equal to dy by dt, or we can say 2x vx is equal to vy. Again, if we differentiate, that will be dvy by dt can be written as, now again two terms are there. So first we have to differentiate one, take other as constant, and then do this again with second taken as constant and differentiating the first. It will be 2x I have taken as constant, this is dvx by dt, and then 2 it will be dx by dt into vx, which is vx itself. So we got square of vx. From here it can be written as ay is equal to 2vx square plus 0, because as we know that it is asking for acceleration at origin, so this x will be 0, and at origin it had started with velocity u, so Vx has to be equal to u, which is our answer, that is equal to 2u square. This is acceleration of particle when it crosses the origin. Now in next part we have to calculate radius of curvature. Since tangential acceleration is 0, so what acceleration we got has to be centripetal acceleration, or centripetal acceleration can be written as 2u square. From here we can write 2u square should be equal to u square upon rho, because v at that particular point is equal to u. From here radius of curvature is equal to 1 by 2. That is 0.5 units. This is how radius of curvature for any curve can be calculated with the help of centripetal acceleration. So far so good.
Let us solve an example more. A train 1 moves from east to west and another train 2 moves from west to east on the equator with equal speeds relative to ground. The ratio of their centripetal accelerations A1 upon A2 relative to center of earth is. See, here it is asking for relative to center of earth. So first let us write the centripetal acceleration. As we know, value of centripetal acceleration has to be equal to v square by r. R is same because it is the radius of earth with respect to center of ground. Both the train is having at the same radial distance. So R will be same for both. But what about V? One train is moving from east to west. As we know that rotation of earth is from west to east. So while writing V for train 1, it will be having value V has to be equal to speed of train with respect to ground, let that be VR plus velocity of ground, but here as these two are in opposite direction, so it will be having magnitude VR minus VG. Whereas while writing V for second train, for first if this is V1, for second let that be V2, V2 will be equal to VR plus VG because these two velocities are in same direction. So if we substitute value of V1 and V2 in place of V, while writing the accelerations, we will get A1 upon A2 to be equal to less than 1 because V1 is less than V2, and so the correct option will be option number C.
One more illustration we can see. An astronaut is rotated in a horizontal centrifuge at a radius of 5 meter. If the astronaut can withstand a maximum acceleration of magnitude 7g, this is the maximum magnitude of acceleration that the astronaut can have. Then what is the maximum number of permissible revolutions per second we have to calculate. Okay, so let us write what is the centrifugal acceleration. Now centrifugal acceleration, as you all must have heard the term, it is just opposite to centripetal, but magnitude wise both are same. So centripetal acceleration, if you see, that will be equal to omega square r. The same is centrifugal, and that acceleration has to be equal to 7g. So its magnitude is 7g. It is asking for maximum number of revolution per second. So let us first calculate omega, that will be 7g upon r and square root of this. If you now substitute the value, g I am taking as 10 meter per second, which is indicated here. So that is 70 upon 5. Radius is given 5 meter. This comes out to be root 14 radian per second. But it is asking for maximum number of revolution per second. So in one whole revolution the angle made is 2 pi. For one revolution angle is 2 pi. So what about this much radian per second? So what about the number of revolutions made if rotation is root 14 radian per second? So it should be divided by 2 pi. So if we get number of revolution, that will be equal to omega upon 2 pi, and on substituting this is root 14 upon 2 pi, that is equal to 0.6 revolution per second. It is the number of revolutions made per second if the astronaut can withstand maximum acceleration of 7g. In next session, I will introduce you to relative motion in 2D. Already we had seen relative motion in 1D and now it's turn for 2D. Okay, bye.